What the hell is enthalpy? Okay, enthalpy is just a funny word for energy. It's chemical potential energy. Now, I've written the definition here, and you do have to commit that to memory in case you have to regurgitate it in an exam. Enthalpy change, delta H, delta means change, is the heat energy transferred in a reaction at constant pressure. Okay? Just looking at the unit, that helps you understand it. It's kilojoules energy per mole, per amount of stuff. So it's basically just energy. Just substitute the word enthalpy for energy in your head, and that will help you understand it. Okay, let's do some examples and it'll become clear. So, this first reaction, barium hydroxide and ammonium chloride. The delta H, the enthalpy change in this reaction, is positive. It's plus 133 kilojoules per mole. Now that means it's an endothermic reaction. When delta H for a reaction is positive, it's endothermic. And when delta H is negative, it's exothermic. Endothermic means that it absorbs energy from its surroundings when it takes place, this reaction, which means it makes its surroundings colder. And there's actually a lot of videos on YouTube of people doing this reaction. Barium hydroxide, ammonium chloride, they're two white solids. It's fairly unusual in that you just mix two solids together without a solvent. But you can watch the videos, they mix them together and put it on a little wooden block. And after a few seconds, they lift up the beaker after the reaction's taken place, and the wooden block comes with it because it's frozen to the beaker, because it's cooled down its surroundings as it takes place. So an endothermic reaction, what that means is the products, all these things, barium chloride, ammonia and water, the enthalpy, the chemical potential energy of the products is higher than the chemical potential energy of the reactants. The potential energy is stored in the bonds between the hydrogen and the oxygen, for example, or between the nitrogen and the hydrogen. So that means that if the products have a higher chemical potential energy than the reactants, energy doesn't come for free from nowhere. That extra energy has to come from somewhere, and it comes from the surroundings. So it takes energy from the surroundings, which is why it makes the surroundings colder. For example, ice packs, when you injure your elbow or something, you stick you snap it to start the reaction off, or shake it or something, and put it on your elbow, and it makes your elbow colder because there's some chemical reaction, it might actually be this exact one, I don't know, that it's an endothermic reaction, so it makes the surroundings colder, it makes your arm colder as the ice pack reaction takes place. Okay, let's move on. So, combustion is an example of an exothermic reaction. And in exothermic reactions, delta H is negative. In this case, it's minus 890 kilojoules per mole. That means that the products have a lower chemical potential energy, or enthalpy, than the reactants. So, that means the chemical potential energy stored in the bonds of these reactants is greater than the chemical potential energy of the products. So that means these are at a lower energy. Where did all that extra energy go? It was released into the surroundings as heat. And as you know, combustion, a fire, releases heat. It's hot. Another example of an exothermic reaction is the Haber process, when you react nitrogen with hydrogen to make ammonia. Delta H is negative, it's exothermic, minus 93 kilojoules per mole. So we're going to look at this one in more detail, and we're going to look at the actual bond enthalpies that are involved. So, nitrogen is, the nitrogen molecule There's 2 nitrogen atoms triple bonded together, so N2 is that, plus 3 H2s. So H2 molecule is 2 hydrogen atoms with a single bond, and there's 3 of them. So this is what the reactants look like. And the products, there's 2 ammonias. So NH3, it's nitrogen with 3 hydrogens on it, and another one here. Okay? So when this reaction takes place, these bonds have to be broken. Okay? That triple bond is broken to separate the nitrogens. They're separate on this side. And same with the hydrogens. These 3 bonds are broken. So that's the energy that's put into the reaction. Energy that goes into a reaction goes into breaking the bonds. And the enthalpy, the chemical potential energy, is stored in the bonds. So in a reaction, you have to put energy in to break these bonds, and then energy is released when these new bonds are formed. And those 2 energies are not always, well, they're very rarely the same. They're different. If you have to put in more energy to break the bonds than you get out when they're reformed, then if you're putting in more energy than you get out, it means it's an endothermic reaction, like this one. But if you put in less energy into breaking the bonds and you get out when they reform, it's exothermic, like this one. And we'll see that in the numbers. So, the bond enthalpy, or chemical potential energy, stored in this bond, a nitrogen-nitrogen triple bond, is 945 kilojoules per mole. Okay, it's 945 plus 3 of the enthalpy stored in an HH bond, which is 436. Okay, so that's the energy we put in into breaking these bonds. And that turns out to be, where is it? 2253 kilojoules per mole. Now the products, we form 6 NH bonds, 1, 2, 3, 4, 5, 6. Okay, so that's 6 times 391. And that turns out to be 2346 kilojoules per mole. You see, they're different. We've put in less energy into breaking these bonds than we get out when they're reformed. Therefore, it's going to be an exothermic reaction. And if you subtract that from that, so you do 2253 minus 2346, that's where the minus 93 comes from. It is minus 93 kilojoules per mole. Okay? So that's how you can use bond enthalpies to work out exactly the delta H in a reaction. Using bond enthalpies is only one way of working out the delta H for a reaction. Another way is using something called Hess's law. Now, before we go into this, we need to go into delta H in a bit more detail. So, delta H is often written with this funny little symbol at the top of it, like that. Now, all that means is that the delta H was measured under standard conditions, which means a pressure of 100 kilopascals, which is about 1 atmosphere, and the stated temperature. Sometimes you see the temperature written down there. It's usually 298, which is sort of room temperature. Don't worry about it. It's usually written, but it doesn't mean much. It doesn't really have to affect your thinking much at all. Anyway, the next bit is that there are different types of delta H. There's the delta H of a reaction, which is written like that. So I've rewritten the endothermic reaction example we had earlier here. So the delta H for that reaction, which is plus 133 kilojoules per mole, that would be written here as delta H R, because it's the delta H of the actual chemical reaction. Okay? Now, there's also delta H C, which is the delta H of combustion. And yes, combustion is a type of reaction, so it doesn't really matter, but you sometimes might have to deal with that. Okay, now, the interesting one is delta H F, which is the enthalpy change of formation. So it's defined as the enthalpy change, the standard enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its elements. And this is tied in with Hess's law. We're forming 1 mole of a compound from its elements. So let's look at our reaction. If you look at all the individual elements which the reactants are composed of, I've written them down here. If you break this down, there's 1 barium, and if you count the oxygens, there are 2 and 8 there. There's a total of 10 oxygen atoms, which is the same, not the same, which in the elemental form is 5 O2 molecules. Okay? Hydrogens, if you count them, there's actually a total of 26 hydrogen atoms, which would be 13 hydrogen molecules. 2 chlorine atoms, that's 1 Cl2 molecule. 2 nitrogen atoms, that's 1 N2 molecule. So, what you do is rewrite the reactants in their elemental molecular form down underneath. Okay? So, looking at the definition of delta HF, the enthalpy change when 1 mole of a compound is formed from its elements. If you could form these in a direct reaction from its elements, like that, then the enthalpy change is delta HF. And that's of the reactants. Just write it as R for reactants. Okay? Right, it's the same with the products here. If you could do a clever reaction and combine all these together to form these, then the enthalpy change would be the enthalpy change of formation for the products. Just write that as P for products. Okay? Now, this is where Hess's law comes in. The total enthalpy change of a reaction is independent of the route taken. Now that means that the total enthalpy change of a reaction is independent of the route taken. So, that means the enthalpy change, if we started here and making these products, by first making these and then reacting in that direction, so there and then there, that enthalpy change is exactly the same, according to Hess's law, of going directly from here to here. A bit confusing at the moment? Let's put it in an equation. That means this route going like there and then there, the total enthalpy change is the same as going directly to there. So that means that delta H F of the reactants, okay, it's that, plus delta H of the reaction is the same as just doing that directly. It's the same as delta H F of the products. Okay? That's Hess's law. So, if we want to find this, we just rearrange to make that the subject. So take this over here and we get delta H of the reactants is equal to delta H of formation of the products minus delta H of formation of the reactants. Okay? And if you like, that's Hess's law in equation form. So we can work out the delta H of the reaction if we know the delta H of formation of these things and these things. Okay? So in an exam question, they'll give you these numbers and you'll have to do this. So I'll write them in. So for barium hydroxide octahydrate, it's minus 3342 kilojoules per mole. Okay, that's the delta H F of barium hydroxide octahydrate. Okay. For ammonium chloride, it's minus 314. For barium chloride dihydrate, it's minus 1457 kilojoules per mole. For ammonia, it's minus 46. And for water, it's minus 286, all kilojoules per mole. So just put these numbers in here and we'll get the enthalpy change of the reaction. So, therefore, delta HR is delta H of formation of the products, so that's this side. So there's one of those, so that would be minus 1457. Don't forget to look at how many molecules that there is of each. There's 2 ammonia, so we have to multiply that minus 46 by 2. Okay, so it's minus 46 times 2. Okay, and there's 8 waters, so we have to do minus 286 times 8. Okay, so that's all of delta HF of the products minus delta HF of the reactants. So there's one of those, so it's just minus 3342. Okay, and there's 2 of those, so it's 2 times minus 314. Okay, stick that in your calculator and you get, plus 133 kilojoules per mole. And that's how to work out the delta H of a reaction using Hess's law. And it's positive, so like we discussed before, it means this is an endothermic reaction, so it takes in heat from its surroundings, makes its surroundings colder. There you go.